Hey, good afternoon, everybody. So as Aries mentioned, I'm Walt Peterson, and I'm a GPM, Ground Validation Science Manager, actually out here in near Traer, Iowa, in the middle of a cornfield with two radars. And I'm just going to show you inside the radar trailer here. So way down there at the end is one of my colleagues, radar engineer from Colorado State, running our NASA D3R radar. That's a dual frequency radar. I run things from a display. I think you can see this is our product output window here. This shows Doppler velocity and return power from the radar reflectivity, and some other polarimetric variables. And then over here, as I swing past my face, whoops, hopefully, yes, okay. So here is a real-time display. That's what we look at as the radar spins, as it's doing right now. Actually, it shows us the returns from precip in the real-time display. And then we've got some power panels and battery packs and that kind of stuff to ensure our backup power. And look like inside the science container. And I'll just put this back down and transfer it back to Aries. Okay.
Thank you so much, Walt, for that tour of the trailer. Let's give it right to our honored guest, Maria LaRosa from the Weather Channel. Maria, you have now a panel of scientists who study rain and flooding and flood prediction. Take it away.
Yeah, this is fantastic, and obviously flood's something that affects people worldwide. And so I want to bring in Pedro to talk a little bit more about the hazard of flood, and what kind of impact we're talking about worldwide.
Thank you, Maria. Flooding is a serious problem worldwide. It is a serious problem in the United States. Among the weather disasters in the U.S., it is second only to heat in the number of deaths, and it is number one in the number of damages, even more than hurricanes and tornadoes. This is on the average through the history. We have a couple of visuals to show what the impact is on number of deaths and number of damages, and value of damages throughout the years since 1903. But it is a worldwide problem. Walt will be able to talk a little bit more about what the impact is worldwide of flooding. For us, the Weather Service, having the opportunity to participate on this experiment, and eventually having the opportunity to receive information from the satellite-based GPM, it will give us a considerable advantage for improving the river flow forecasting. We have an extensive network of radars throughout the world, and we have another visual to display that even though the network is very widespread throughout the U.S., we have 150 radars. There are gaps in the coverage, especially at the lower elevations. That, having the advantage of the satellites looking from space down into Earth, will help us fill those gaps and improve the forecasting of river flows.
Wonderful, thank you. I want to remind our audience that you can please ask us any questions about floods or flood prediction here in the Google chat, on YouTube, if you're watching on YouTube, in the comments section, or if you want to send us some questions through Twitter, just use the hashtag iFloods, that's the letter I, and then floods with an S. Moving on a little bit, I'd like to ask Vitek a question. Now, one of the things that this particular ground campaign is focusing on is Iowa, and I know you're out there in Iowa, Vitek. First of all, why are you focusing on Iowa of all places, and then what is happening out there with this ground campaign?
Yes, well, this is a natural question, why Iowa? Well, the simple answer would be because we've got floods. And it is true that our state got its share of flooding over the last several years. In 2008, we had an extreme event that cost the state close to $10 billion. And at that time, the value, if you will, of that disaster ranked the fifth costliest in the history of the United States. So we're talking, real money. And in particular, the city in eastern Iowa, the city of Cedar Rapids, was affected in a terrible way. Some 1,000 city blocks were inundated by that flood. The flood came on very suddenly. It was a case of a traffic jam in the river network. There was already a flood wave moving downstream, and that coincided with a response to a torrential flash flooding, event, and the two collided, you can say, downtown Cedar Rapids. And so, but this was not the last, flooding in Iowa. There were floods in 2010, and then many of us remember the flooding on the Missouri River, which is one of our border rivers. That lasted for several weeks. And even now, as we are in the middle of this field campaign, we've got flooding over the last month in several places in Iowa, including here in Iowa City, where I'm speaking from. So and still the rivers and streams are running high. Which of course makes for a good case for scientific study, but I wish that that flooding would stop. We got enough.
Excellent. Thank you so much, Witold. I'm wondering, so what do you need to know to make a flood forecast? What's the exact data that can lead to being able to forecast it? And is this like the weather forecast we watch in the nightly news every night, where it's like chance of sunny, partly cloudy, that type of thing?
Well, you have to watch the conditions over a longer, period of time. So what is very important here is the scale. So for small scale, very small, watersheds, there is a very quick response to any heavy rainfall. But as the scale increases, then that connection between the rainfall and the response, and again the response is in the form of the amount of water that is moving through the system of streams and rivers. That connection is a little bit less obvious, and I can give an extreme example here. So imagine yourself in New Orleans, and then there is a severe storm in Iowa. Well, you don't see the immediate effect of that storm in Iowa when you are hundreds and thousands of miles, away. But the two are connected. That water eventually will find its way all the way down, to the outlet of the Mississippi River Basin. So again, it's an issue of scale, and of course, rainfall, especially large amounts of rainfall, that's a necessary ingredient, and how the ground responds to that rainfall, whether or what fraction of it will infiltrate, and what fraction of it will find its way to streams and rivers. That is, determined by land use and the soil properties. But after that, it is the transport in that river network that determines the timing of the flooding and its extent. So it's a complicated, phenomenon, and you have to have a good handle on all these, conditions to be able to make a good prediction.
I wanted to ask Vitek and Walt and Pedro, it's very complicated forecasting floods. What do you gentlemen see as good aspects to what we have now, and then how can things like satellites improve forecasts?
So perhaps Pedro should take this one.
Hi, Pedro, take it away. I think we're having a problem with your mic.
Yes, we were. The main advantage of precipitation from satellites, well, there are many advantages. One of them is the global coverage. It goes throughout most of the world, given the satellite constellation has a near polar orbit. So areas of the world that are not currently covered by observation of precipitation, especially the oceans, or many countries that don't have the radar network that we have in the US, now will have the possibility of having near real-time coverage of precipitation and severe precipitation issues. It also has an advantage of enabling quantifying the overall water cycle by observing precipitation in areas that have not been observed so far. They will be able to tell how much precipitation, what intensity of the precipitation is, and how often the precipitation is happening, and then use that to corroborate the predictions that the global climate change models are coming up with. So the advantages are absolutely multiple, and even in the US, with all our network and our sensor, we will be able to take advantage of that new facility.
And now, Walt, how does that lead into this upcoming NASA mission that we have launching, the Global Precipitation Measurement Mission, or GPM?
Yeah, that's actually a perfect lead into GPM. So the Global Precipitation Measurement Mission is an international mission, satellite mission actually, slated to launch the core satellite in February of next year. And so the GPM mission is really designed to do the global energy and water cycle, and to by virtue of our enhanced ability to measure precipitation in a global sense, enable us to do a better job of predicting natural hazards like flooding. So there's the water cycle aspect, and importantly also a weather and climate aspect to GPM. So the information that we collect from the satellite mission itself is used to improve our ability to do numerical weather prediction, which is important to be able to sort of describe conditions upstream so that you do a better job of predicting downstream in an atmospheric sense when you're going to have heavy rain events in that. And then also our ability to, our improved technology and instrumentation that will be on the satellite itself will enable us to do a better job of accurately measuring rainfall rates. And of course, this all goes back to societal applications and our ability to take the information and better help decision makers and people that issue warnings and or decide whether or not they're going to irrigate their field today, for example. That's what GPM will, the capability that GPM will provide us, and do so over sort of a more global scale. Pedro talked about the issues of flooding and some statistics in terms of impacts in the United States, and we do see, though, that the largest impacts from flooding are really more out there in the developing world. In particular, you know, tens of thousands of people annually lose their lives to flooding, the overwhelming majority of that being in the third world. And it's also, from a dollar, sort of a dollar cost perspective, much larger impact in developing nations, and mainly because I think really of the warning aspect and the ability to inform people ahead of time of when we're going to have flooding issues. So GPM will help with some of that, and I don't know if at this point you want me to describe more about the mission itself.
Well, actually, I was wondering, as part of talking about the mission itself, GPM, we said it's new, but it's actually the next generation of a previous satellite right out there, something called TRIM, the Tropical Rainfall Measurement Mission. Am I right?
That's correct. Actually, GPM will significantly extend the capabilities that we developed with the TRIM mission. The TRIM measurements involve both a precipitation radar, a single frequency precipitation radar, and an advanced multi-frequency radiometer, and those things have worked great basically at letting us see rainfall in the tropics, and in fact a lot of those information are used in real time to improve, for example, tropical cyclone fixes. So when the satellite flies over, you get a really precise fix on the center of a tropical cyclone or even a developing tropical cyclone. The radar itself allows us to map the depth, the three-dimensional depth of the precipitation And from that, we get some indication as to whether things are developing or intensifying even more in a tropical cyclone. So GPM kind of follows on the TRIM mission and then extends it by virtue of the new technology and also the fact that now we're talking about a constellation of satellites with GPM. So GPM, the core satellite, is one platform that we launch next February, but there are actually already satellite platforms up there that will join the constellation of the, that comprise the GPM constellation, with the core satellite acting as the on-orbit calibrator of that entire constellation. And then we increase our sampling to like 1 to 3 hours for global precipitation maps, compared to TRIM right now, which gives us sampling in most locations on the order of twice per day.
Fantastic. I just wanted to jump in, and we're going to be saying your questions that are coming in through YouTube, through Google+, and also through Twitter in just a few minutes. If you're following along and want to ask a question on Twitter, it's #iFloods. That's the letter I and the word floods with an S. And after this Hangout airs live, it's going to be rebroadcast and archived on the Goddard's YouTube channel, which is NASA Explorer, and we'll provide those links as well. We'll also provide some links to all the different videos and things that we're showing throughout this Hangout. And joining us just right now, we've got Walt Peterson, who's with NASA Goddard Walt's flight facility. And if Walt looks a little darkly lit, it's because he's sitting in a trailer out in the field doing a ground campaign for this new satellite that we're discussing that is going to hopefully give us really great insights into rainfall and be able to connect it back to floods. There's a lot of flooding going on. Here on the East Coast right now as the remnants of tropical storm Andrea goes up. And then I know in Europe, in Germany and Eastern Europe, are having the worst flooding they've had in decades. So I'm going to give it back to Walt to talk a little bit more about this mission and how the details that it's going to be collecting will help feed into flood forecast predictions.
Oh, were you going to hand that back to me or to Pedro or maybe VTech?
Why don't you start, Walt, and then we'll go down the line.
Okay, so the information that the mission collects, the fundamental measurement is the rainfall rate. The rainfall rate is kind of a fundamental input into a flood forecast model. The flood forecast model uses other information as well as the rainfall rate, things like the state of the ground, how moist the ground is, which determines how much runoff or filtration you have, and actually possibly VTech might want to chime in on that aspect of things, being a hydrologist and flood modeler.
Yeah, let me continue. So the big issue here is that although GPM satellites will provide estimates of rainfall rate, these estimates are just that, estimates, and so then there is a question: how good are they, and what kind of capabilities will we have with using then hydrologic models and that GPM rainfall input into prediction of floods. So because as we all know, and probably Maria the best, predicting what nature will do is not always that easy, quite challenging in fact. So so one big goal for the research associated with the GPM is to figure out at what scale the GPM rainfall estimates or maps will be appropriate to make skillful predictions of floods and other natural rainfall-induced hazards such as landslides. So this is a big goal, and that's why it is important to have a good reference data set on rainfall all the way from tiny little scales at a single hill slope all the way to the scale of several thousand square kilometers, and this is what we've got here in Iowa. We have very well instrumented watersheds. We have a plethora of instruments, not only NASA radars but other radars that are operated by the National Weather Service, some additional research, radars, a bunch of other instruments measuring not only rainfall but also stream flow and soil moisture. And it is with all these ingredients then hydrology researchers who develop and test hydrologic models will be able to answer this question. So, for example, right now you are looking at this graphic of how water travels through a watershed. So we see here the Cedar River Basin, and to the north the larger one, and the Iowa River Basin. And the zone of the travel time, if you will. So it takes, if you count the different colors, it takes about a week, 8 days for rainfall to travel across this watershed. And so with all this information that we have been collecting here in Iowa, then a much larger community will analyze, the data and improve the flood, prediction worldwide.
I do have a question for Pedro, Walt, and Vitek. You guys are talking about the global scale and what this will mean for global flood prediction, but you guys are starting on a smaller scale in Iowa. We've been talking about that. Can you guys go into some detail of the actual components you guys are using, the rain gauges, and how you're using all of that information, ground truth versus what you are seeing on the satellites right now?
Right. So the idea here is that, GPM, we're claiming that we're going to make these measurements globally, and of course that also means locally by implication. The question is, how accurate are those measurements, and then going beyond how accurate are those measurements, if they're not that accurate, how do we make them better, how do we improve them? So we do field campaigns like what we're doing in Iowa right now, and Vitek discussed a bit about the instrumentation there. But the idea is to really connect what we're measuring at the ground to what we're seeing from space. And so here in Iowa, we've deployed a bunch of instrumentation in addition to what the Iowa Flood Center and other agencies like NOAA, the National Weather Service, the U.S. Geological Survey, et cetera, already have in place. And those include things like rain gauges, and there's an image right now that you see that has, those are dual rain gauge platforms that we're using. We've deployed a large number of those actually in networks around Iowa in specific river basins like the Turkey River Basin up to the northeast, the South Fork Basin, which is part of the Iowa River Basin to the west. The idea there is to use these gauge systems with also attached soil moisture probes and temperature probes to connect the rainfall at a very local scale, or sort of use it as a calibration source, if you like, at a local scale to compare to the broader measurement which we do with radars. And so there's an example of one of the University of Iowa X-pole radars. So this is one of the radars that we have in the current network. And then the NASA radars that we've deployed include the NASA N-pole radar, and I don't know whether we'll be able to get the graphic up there or not of those radars. But either way, we use the rain gauges as kind of this point measurement source that we take as almost the gold standard. When we have those two rain gauges together, then we know that we're getting an accurate measurement of the rain at the rain gauge location, and then we scale up with the radars. So, for example, the N-pole radar, which is shown there, I don't know if the movie will work there, but we use the radars like the N-pole radar in the network to scan on a much broader domain. So the N-pole radar is looking out at scales on the order of 100 miles or so to map the rainfall near the surface on a scale of, say, 1 kilometer or so. And we use that measurement, we use the rain gauges with some other measurements we're making of individual, for example, raindrops to reference the radar. And so here, this is an example of the radar scanning in what we call a PPI mode. So here's how we would map it in the horizontal by spinning the radar around in the horizontal plane to map the rainfall. We make a rainfall estimate from this radar. This is a dual polarimetric radar, which makes fairly accurate measurements of rain on the order of 10 to 20%, for example, on an hourly accumulation basis. And we take those estimates as a reference, and we run them into a hydrologic model that, for example, VTEC or Pedro would run, and that gives you kind of a stream flow, an estimate of the stream flow or an output for a given. And what we do is call that a reference stream flow based on our reference rainfall estimate that we assume to be accurate to within some degree, and then compare it to satellites that are currently overflying the site, every day, several times a day, several satellites. And from those measurements, then we can connect the accuracy with what we get at the ground to what we're seeing from space and say, all right, well, we're off by maybe 50% from space. We don't know that yet, of course. So we haven't finished the experiment. But if we're off so much, we might be able to estimate, sort of why, or guess at why we're off so much. And here's an example of a graphic that shows in the top a satellite estimate from the case we sampled actually on May the 20th during the iFloods field campaign, compared to the ground estimate provided by the Iowa Flood Center. And you can see that, the comparisons are, broadly consistent, but in fact, there's a big difference in resolution between what the satellite sees and what we measure at the ground. And then there's also some basic differences in amounts that indicate, hey, we can do better from space. And so as we make the measurement at the ground here with the radars, for example, if we interrogate the storms a little bit more with the radars, sample them in the vertical plane, we start to learn about how the storms are constructed in the vertical, and that's very important from the perspective of a satellite, because a satellite is looking downward at the surface of the Earth. So what it's seeing is the surface of the Earth and then everything in the column that's between it and what the satellite measures. And so with the radars, with the research radars, we do a lot of work looking at the clouds in a great bit of detail in the vertical to learn about what the precipitation is constructed of, whether it's ice or rain, and then how the process works to make the rain. And a lot of that contributes to some of the differences that you see in the rainfall maps there. And so that's what we're trying to achieve here in iFloods, is connect everything that we see at the ground, which we consider, basically that's reality, to what the satellite is inferring is going on from space. And you take all that information and put it together, and that should help us really improve our ability to use those spaceborne estimates worldwide. So, so there's the global or the local application, but or the local study, but global application. So we truth ourselves here in Iowa, and then hopefully do a much better job globally, especially in countries that don't have access to all of the resources that that we do here in the United States.
Excellent. That leads really well into one of the first questions we got from online. If anyone's watching, please put questions in YouTube comments or on the Google Plus page, or go ahead and use the hashtag iFloods. That's the letter I, the word flood with an S. And the question I've got right here, it's by Anil, and it came in through YouTube. And are you going to be, her question is, does the flood data get fed into a public information system, or is it given to weather channels? I know, Walt, you talked about this a little bit. Are you going to be setting up a whole new system for flooding, or is it going to be feeding into places just for scientists to see? Or are you going to be feeding it to people like our guest Maria La Rosa from the Weather Channel, so they can go ahead and give people straight out flood predictions? Right.
So all of the information that's collected by NASA satellites, by the GPM satellite, actually will feed into our national flood prediction systems to folks like Pedro and VTEC. Actually, those data are available, or will be publicly available, to just about anybody that wants them online. There's about my understanding is about a 1 hour lag roughly between the time the data are collected and products are made and distributed, and then they would get shifted off to folks like Pedro for putting into their models. And I don't know if maybe Pedro would comment on how that would work once the data were handed off to NOAA.
Yes, Walt. Right now we get information from our network of radars, from rain gauges on the ground that are operated, some by us, but the majority are operated by the United States Geological Survey, some by the Corps of Engineers. and some by other federal, state, and municipal agencies that share that information with us. We also have a network of cooperative observers that take daily precipitation data and send that information to us. That's part of the ground validation for not only the satellite, but also for our own radars and our systems. Once we get information from GPM, that information is merged with the rest of the observations that we have from the ground and from our network of radars into a single coherent product in what we call multi-sensor precipitation estimation. And there are several versions of it. One is being developed by the National Severe Storm Laboratory in Norman, Oklahoma. That will take precipitation from satellites merged with the radars and so on. That having 1 hour lag is really not a big deal for us. We issue our precipitation forecasts every 6 hours during flooding conditions. We may issue more often depending on the circumstances. So the 1 hour just fits perfectly well within the time frame that we have to get our forecasts out. So again, filling the gaps, having information that before the satellite we are not able to get because of the lack of coverage by the radars, by mountains being on the way and obscuring part of the radar beam, it is most welcome for us to improve our forecasting.
Great. Just reminding everybody, I'm Aries Keck. I'm here at NASA Goddard Space Flight Center in Greenbelt, Maryland, and we're talking about floods and flood prediction with our panel of scientists and Maria LaRosa from the Weather Channel. You can send us questions through YouTube comments, on Twitter at #iFloods, that's the letter I, and floods with an S, or on the Google Plus Hangout. We got a question here from YouTube comments. GT Stamak asked, why is GPM not geosynchronous, and what advantage does this give it? Vitek, I know that your specialty is using precipitation radar and satellites. Could you answer that question and first remind people who may not be scientists what we mean by a geosynchronous orbit?
Yes, well, this would be a very good question for Walt, but I'll give it a shot. Different satellite platforms are at different distance from the Earth, and the sensors that they have on board operate at different frequencies. And then the resolution of data collected, and of course we are interested in the resolution near the Earth surface, depends on those two factors. How far you are, or how high in this case, and what exactly is the frequency that you are listening to, so to speak. But there is another factor, and depending on that frequency that your sensor operates, you see different things. And so for example, if you are operating at the visible light frequency, well, you see what we see with our own eyes. So you see, for example, that there are clouds there, but you do not see what is below the clouds. And so now if you are working at another frequency, the infrared frequency, so we know that is that the signal corresponds to the temperature. So now if you are looking with such a sensor at the cloud systems, you can tell a little bit about the temperature of the cloud tops. So again, that gives you some information about how high the clouds are, and therefore how vigorous are the processes below the clouds. So that may give you some hint regarding the possible amount of rainfall that is below the clouds, but you don't really know that very well. So then there is another range of frequencies, that the microwave frequencies that correspond to the signal that is emitted by liquid water or ice, and so now you are really below the clouds. But because of that, frequency, if you were in a geostationary satellite, your resolution would be extremely, poor. So you want to get closer, to the Earth, surface to have, decent resolution, like few kilometers, on the side. So those are the interplay of all those, factors, determines, the choice for the location of the satellite. And but here I would like to add that we still have geostationary, satellites up there, and it is the combination of the data from all these sensors that makes for the best, possible rainfall mapping. So I hope that I answered the question.
I have another question. I think one of the great things about being a scientist is getting excited about things that perhaps you didn't expect. So is there anything in the data so far that's been coming in that you guys have been looking at, analyzing, that has surprised you, excited you about any kind of breakthrough about what the technology is going to do for the future? Pedro or Walt or VTech?
Well,
Walt, why don't you take it away?
Okay. So I think one thing that's been kind of interesting about this particular experiment, at least, is that we came out here with aspirations of sampling heavy rain, and we certainly have had that. There's no question. I don't know that we've seen anything surprising with respect to what we expected to see for the rainfall process itself. But I will say this. When we came out here, we brought multiple frequency radars here. We've got, all kinds of frequencies of radars. And so we came out, to sample rain, and we started off, however, with a historic snowstorm. and and that actually gave us a great opportunity, believe it or not. We were just up in Canada a year ago doing a snowfall experiment, because, of course, GPM is going to do snowfall as well. This was the first time that we actually could sample an event with snow, mixtures of snow and rain, mixtures of ice pellets and snow and rain, a really complex weather event, actually, right when we got out here with our dual frequency radar at the same frequencies, actually, that'll be flying on a satellite in February, and a radar like the NPOL, which has a completely or a much lower frequency and longer wavelength. And that's really important because it enabled us to see some interesting signatures in the precipitation itself and the different layering of the precipitation, the complexity actually in the vertical. That's going to be actually quite critical to how we interpret what it is we're seeing from space with the radar in space. And I think that perhaps that will be an event that we weren't anticipating, but that will be very useful to us in terms of trying to figure out how we deal with precipitation like that in the mid-latitudes. On both the northern and southern hemispheres. So that was actually kind of neat.
Well, let me just add that this has been an extremely busy, campaign. So we had very few days with no rain during the last, 5 or 6 weeks. But when we were planning, the campaign, when NASA was making the final decision when and where to host it, to conduct it, here in Iowa, we were in a severe drought, and so of course, so then. What I was saying, earlier, that here in Iowa we've got, floods. So last year it was not true at all. We were in a severe, drought. So things turned out quite a bit. And again, not only that we got, plenty of rainfall, data, but we also got some flooding. So we will have a very good information to analyze that entire, cycle from rainfall all the way to flooding. So
we're getting a number of questions on YouTube and other social media channels, more sort of asking, shouldn't people just move? And I'm wondering, you know, it's not exactly a question for exactly your rainfall studiers, but I'm wondering if you see places that do get flooded time and time again, I mean, how good is prediction if you can't really well move your house around? I'm wondering, people know that you study flooding, do you get those questions quite a bit on just that aspect of where people live? And what do you answer to that? I'll throw it to Pedro first.
Well, you throw me the difficult one. I personally would not live in an area which is prone to flooding. Okay, I would not live in an area that is downstream of a dam.
Right from the expert.
Oh yes, oh yes. And if the predictions from the climate change come through, we are going to see more incidents of flooding, although there's no evidence yet that we are seeing that the frequency of flooding has increased. But as the century goes on, if those predictions come through, we're going to see more incidents of flooding. A single event just cannot tell you that climate change is being confirmed. But once you start to see that frequency again, still being repeated every 20 years or every 50 years, they come every 10 years, every 15 years, and so on, then it tells you that you have to take other actions. Protect your permanent protections for property in the forms of levees has some advantages, but it also has some disadvantages. The fact is that it actually creates a superhighway for the flood to go through. Instead of having the flood spreading through the floodplain, it goes through, it goes much faster, and it is stronger. So there are plus and minuses of those defenses, and there are other possibilities, like, for example, what the Dutch do. They have been fighting, as we know, the sea for centuries, and in their case, when they have river flooding, they know which areas will be deliberately flooded to prevent further damage downstream. So the people who live in those areas already know that what is going to happen. They are prepared, and they are also prepared to be compensated by the damages that they occur. If you remember, on the Mississippi River last year, there was, on purpose, one of those levees was breached, and it actually, you could see how the surface of the water dropped in response to that. So this is another management technique. But if I were to answer the question, if I were living there, I would move to higher ground.
We have a question from a teacher. I hope she's still watching. I'm going to, unfortunately, I'm sure, butcher her name. Maria Lorraine de Ruiz Alma. And she says that she believes in the power of community and is wondering if we can locate lots of rain gauges in areas around rivers, of places that can be affected by floods. You'll be having more accurate data, and that'll represent all the microclimate variables, and will help the community make better and faster decisions and actions. Walt, I know that one of the reasons that the GPM, the Global Precipitation Measurement Mission, is deemed so exciting is because people think of rain gauges as being everywhere, but they're actually, if you look at it worldwide, there's not many rain gauges anywhere. And hopefully using a satellite, which actually circles the Earth, will be able to give us more data. Can you sort of draw that out a little bit more?
Sure, sure. So, right, so rain gauges have long and history for this this type of application. The interesting thing, though, is you know, you're talking about, you know, a 4-inch to 8-inch type gauge, and if you took all of those reporting gauges globally and you sort of gathered them all together, basically you'd fill up about 2 basketball courts of area, which, you know, that's not, you know, that's a relatively small fraction of the Earth that you're sampling with just rain gauges. Okay. And
wait, this is yours. 2 basketball courts. That's all. Everything in the entire world.
Well, yeah, that's, you know, that's the gauges we know about. Of course, there are others, and actually, you know, one gauge is really actually representative of a different sized area depending on the amount of time that you accumulate a rainfall estimate, for example. But really, it's a very small fraction of the Earth's surface. And then, of course, you have to account for the fact that, you know, 3/4 of the Earth's surface is ocean, and we don't have that many rain gauges sitting out there on the ocean. You know, there's some on buoys and such, but there's not a lot of rain gauges out there. So you go from a rain gauge, which is your point estimate, to a radar, which gives you a much broader area measurement over, a domain of 10,000 square kilometers, and at a relatively fine resolution. But you have issues sometimes with accuracy on a radar estimate. And then you move up. If you want something globally, the only answer to really get you to that global scale is a satellite, and really to give you that uniform measurement also. It's a satellite. That's what you have to use. And so that's kind of how that works. And rain gauges are great as long as you take very good care of them, check them regularly, because they get filled up with leaves, and birds tend to like them for using the bathroom in, for example, making nests in, things like that. You really have to pay attention to what you do with your rain gauge, where you locate your rain gauge. It's very specific things that actually make a rain gauge or help a rain gauge give you to get a valid measurement. So these are all things that argue for a remote sensing application like a satellite.
And Walt just showed some of the beauty of being on a field campaign, of emptying out rain gauges full of birds' nests and other things. We have a question that came in from YouTube by Jason Blumfeld, and I believe it's more for VTech. His question is, could the excess flood water that comes in during a flood be infiltrated into aquifers or help irrigation in dry areas? Is it possible to manipulate water on such a large scale? I mean, we know that we have dams all across the world, but I'm not necessarily sure if we use dams to work with flooding. Vitek, is that a question for you, or maybe Pedro?
Yeah, I'll be happy to address this question. There are many reservoirs that are built around the world specifically for this purpose. So there are reservoirs that are built for flood protection, but many of them have multiple purposes of providing electricity or for providing water for irrigation, providing water for recreation. These are very large and complex and expensive systems that help us manage water resources. We have many of those in the United States, and there are many famous ones around the world. So that concept is not new. Nevertheless, I myself, thought about, this very question a couple of years ago, where we were experiencing a prolonged flood on the Missouri River at the same time when Texas was experiencing an extreme, drought. And I thought that the states that border the Missouri River, South Dakota, Nebraska, Iowa, Missouri, that they could have made a lot of, money if they could transfer that water to Texas. But of course, such a system is not, in place. So, and it would be perhaps, detrimental to think of this for many other, reasons that we really don't have the time to go into. But we do have such systems that help us manage water resources.
I have a question or slash statement, and kind of want to see what you gentlemen are thinking about. We were talking with Pedro, talking about, do we move people who are in these flooded areas? Do you choose to live there? Do we force people out? But also, Vitek, you were talking about Cedar Rapids several years ago with the big flood there, and having a little bit more time with a better forecast could have saved billions of dollars. I immediately thought about the Red River flooding this year in Fargo, where the forecast was very high, near record. It ended up being several feet below, and instead of losing money due to loss of property, because now the flood wasn't as bad, you were losing money because you had all these man-hours put into making all these millions of sandbags that never got used. perhaps lost tourism, that kind of thing. How do you feel about the importance of better forecasting in that regard? Not so much saving property from floodwaters, but actually saving man hours and that kind of aspect.
Yeah, I think this is an excellent question for Pedro.
I agree. Well, I'm glad you asked the question, Maria. The river forecast in Fargo is probably the most difficult that we have in the entire area, and we have a very large area to cover. The problem in Fargo, or for the Red River, is that the hydrology is complicated, because you have the problem of the frozen ground, we have the problem of a drought preceding during the summer and the fall. Then we have a considerable amount of snow in the spring and in the winter and spring, and there was no way for our models to be able to consider those particular circumstances. We don't know some of the effects of the man-made modifications to the watershed. For example, there's an extensive practice right now of installing field drains at farms. We do not understand what the effect of that is on the hydrology, and our models certainly don't have that. For you to have an idea, one of the small watersheds on the Red River, the headwaters, the Bois de Sioux River, that's the only one that really requires permits for the installation of field tile drains. On that watershed alone, in the year 2012, there were 7,000 miles of tile drains installed. If you compare that with the size of the city of Fargo, which has about 500 some odd miles of streets, that'll tell you, give you a way to compare how large and what a great impact those tile drains could be. We are working with the Corps of Engineers in improving our ability to forecast on the Red River. And you are absolutely correct. Savings is not only the property that you save, but also the manpower that you save by not having to fill those sandbags. The city of Fargo spent $3 million and the Corps of Engineers another $3 million in temporary protection, because our models were forecasting a much higher crest than what actually was observed. So hopefully in the coming years we will be able to improve our models and improve our knowledge of the conditions there, so we can save the city of Fargo and the other communities, not only on the Red River, but also across the board in unnecessary protection measures. The other side of the coin, though, is if we had under forecast and the river had gone way over, too late for any protective measures, then the damages would have been not only in the millions, but also in the billions, which is what happened in Grand Forks back in 1997.
Excellent. We have time for just, I think, 2 more questions. We've been getting questions in through YouTube, through Google+, through Twitter at our iFloods hashtag, and then, of course, from our guest Maria La Rosa from the Weather Channel. One of the questions that we have that we wanted to make sure we get to, and I know we're almost out of time, but it's a question for Pedro, and it's heavy rain is the cause of most flooding, obviously, and this is going to be predicting flooding. What's the status of predicting landslides that are triggered by rain? Landslides are clearly one of the most deadly aspects of this, especially in the developing world. Pedro, how can you possibly use this to work in predicting or determining or even just studying landslides? They're very sudden effects as far as I can tell.
Well, it is a very good question too, and it is a very difficult problem. We have jointly with the USGS a program for forecasting debris flows, which is the technical name for what people know more commonly as mudslides. Debris flows are a type of landslide that occur suddenly during heavy precipitation events, but it is particularly serious for the areas that have been subjected to forest fires, mountainous areas of the forest fires, because the ground is left without protection, and the heavy precipitation that will fall on the burned area will cause landslides. what makes it very difficult to forecast is that in contrast with flash floods or common floods, where we know that the flood occurs at the bottom of the valley, landslides occur anywhere on the side of the mountain, on the hill. It can occur anywhere, so it is very difficult to forecast where exactly that's going to happen. It is a fact, many factors. So the USGS is currently working in improving the models that will be able to tell, working jointly with us, with not only with observation but also with forecast, on what these landslides will occur.
Wonderful. And then I'm wondering, that falls nicely into, and we've talked about this a little bit, but how this information is going to get out to emergency management people, to weather forecasters, to things like that. We've talked a lot about how GPM, the G stands for global, and in this particular ground validation campaign is very, very local right there in Iowa. How are we going to go back and forth? And Pedro, it looks like you've got an answer.
Yeah, well, and I forgot to mention too, for landslides, because that was the connection to the question, GPM is going to be vital for landslide forecasting because it is going to be covering areas in the mountains that are not currently covered by the radars. Okay. Now about the forecast worldwide, we have at the Weather Service, we have a contact with the weather services, or essentially of all over the world through the World Meteorological Organization, and I'm sure that NASA will have something similar too, on the ability to get the forecast and the observations on time. So I'll let Walt complete that response.
Yeah, actually, I would just add to Pedro's response there that, in fact, the NASA Precipitation Measurement Missions science team actually has funded a couple of studies, a couple of researchers to look at actually constructing landslide models for more global applications. And I think that application right now is in its infancy. But actually the systems are somewhat together, and so as we move along here with GPM and get better with things, I believe we'll have these global landslide monitoring and prediction systems in place, which is fairly important. Even though we're not maybe that great at forecasting it now, we will get better, and the infrastructure will already be in place to do it. So that is something that NASA is always also looking at.
Well, thank you so much, everyone, and thank you, everyone who's been watching this Hangout as it's been airing live on Google Plus and on YouTube. This Hangout's going to be archived in YouTube at the Goddard YouTube channel, so anyone watching this later, thanks for watching it later after the fact. We've been talking about floods and flood prediction here in this Hangout, and joining us has been Vitek Krajewski from Iowa City. He's the director of the Iowa Flood Center. In Minneapolis, Minnesota is Pedro Restrepo, the hydrologist in charge for the National Weather Service's North Central River Forecast Center. And then Walt Peterson, who is leading our NASA team out in Iowa. Walt's been joining us from a research trailer in Iowa, so if his video has been a little sticky, that's why. And then also we've been joined by Maria LaRosa from the Weather Channel. You can follow along on everything happening with the iFloods campaign and everything else that NASA's been doing in studying storms and rainfall and snow from space and from ground validation programs at NASA Goddard. We also have a particular Twitter channel that focuses on rain. It's at the @ NASA_rain. Again, that's at NASA_rain. And even though we called it rain, it also covers snow, hail, and all kinds of other precipitation. Thanks so much for everyone joining us, and thanks again for joining this Google Plus Hangout.
Thank you.
Thank you, Bob. Goodbye.
Thank you.
Take care.
Thank you. Bye-bye.